All right. This is one of my favorite lessons in Algebra 2. Because today,
Is it really easy?
Did the arrows come up with a fundamental theorem?
did what?
Did the arrows come up with a
I have no idea.
They're often for the whack. They're often called the foundation.
What? You're so random.
Hey, just
All right.
Henry's fun fact number one. Don't worry, there's more fun.
That's supposed to be a fun
So today's lesson is about the fundamental theorem of algebra. Like, doesn't this sound like
fun.
if I get today's lesson, all secrets of algebra will be open to me? I mean, it's the fundamental theorem of algebra. Like, this is the foundation upon which algebra rests, right? I mean, this just sounds like important stuff. We get this, and the rest of class is a breeze. So here's what the fundamental theorem of algebra says. If f of x is a polynomial of degree n, where n is bigger than 0, so basically anything that's not a constant polynomial. There's got to be some variable in there somewhere. Then the equation f of x equals 0 has at least one solution in the set of complex numbers. Bam. You feel smarter?
No.
It cracks me up every year. I've been teaching for 27 years now, and every year I just have to giggle to myself when we get to the fundamental theorem of algebra, because it sounds like it should just be like earth-shaking, you know, like this is it. This is what algebra is all about. And then you read it and you go, what? This is the big deal? Like, this is the fundamental theorem? It basically says if you have an equation, a polynomial equation, that you set equal to 0, as long as the polynomial is not constant, you have to get at least one solution. Really? Wow. That's no kidding. Okay? Now, the little bit of significance, I guess, to this is the fact that we are talking within the set of complex numbers. So we do sometimes get those equations where we try to work them out and we say, nope, sorry, this one's a no solution. But that's because we're working in the realm of real numbers. So in order to be able to say this, we do have to expand out to the complex numbers. We have to include our imaginaries and our i's and our a plus bi's and those kinds of answers within the set of what our solutions can be in order to be able to say this. Okay? Now, probably what's more helpful to us in what we're doing this chapter is the corollary to this theorem.
It's like geometry.
Yeah, a little bit. But I won't ask you to actually memorize them. Okay? But you do need to know what they're telling us and what they're allowing us to do. So the corollary is actually a bit more helpful. And the corollary says that if f of x is a polynomial of degree n where n is greater than 0, same setup, then the equation f of x equals 0 has exactly n solutions, provided that each solution repeated twice counts as 2 solutions. If it's repeated 3 times, it counts as 3 solutions. And again, we're counting reals and complex. And so if you really go all out and you take a polynomial and completely solve it, all the way down to its complex answers, you are going to end up with the same number of solutions as what your degree was. So if you had a third degree polynomial, you better be getting 3 solutions. If you had a 5th degree polynomial, you better be coming up with 5 solutions. Now that wasn't necessarily the case in the lessons up till now, because in those lessons we were still focused on solutions that were real numbers. So if we ever came up with a situation where we got the imaginary answers, we did not include them when we were asked for real number solutions. But now we're saying we're going for everything. Reals, complex, imaginaries, every possible solution that we can get, we need to find it. And then there's this hint to the fact that, and sometimes solutions show up more than once. So even though we may only list it in our final answer once, the fact that it repeated means we really count it twice, or we really count it 3 times toward the total number of solutions. Okay? So we're talking about 2 different types of solutions now. We're still looking for our real solutions, which include the rationals and the irrationals, which means we still can use our rational 0 theorem to get that starting list, right? To get the numbers that we should start out with and start by testing. So we're still going to set up our rational possibilities. We're still going to test those to see which ones work. And it's usually when we get down to that quadratic step that we end up with the other stuff. We end up with things that are irrational. We end up with things that are possibly imaginary. Okay? But this is what we're most interested in, is the fact that whatever my degree is for my polynomial, that's how many answers I better end up with. Okay? So, now our directions are going to ask us to find all zeros or all solutions to our polynomial functions, not just the real ones. So if we have something like this, where f of x is equal to x cubed plus 5x squared plus 4x plus 20, our first step is just like it was last lesson. We're still going to figure out what are the possible rational zeros first. So what should they be in this case? Okay. And for homework, I highly encourage you to use your calculators. Okay, where's my, there it is. Sorry?
Can we just split the equation that we were doing in half?
What do you mean by split it in half?
Not half, but like we round.
Oh, take out x squared.
Do the grouping?
That makes sense.
Would this be one we could do grouping on?
Take x squared out of the first one.
Yeah. So if you get a polynomial where you notice that, you know what, there's these 4 terms, and if I group them together, I actually would get parentheses that match up, then yes, grouping is totally fine. Okay, so let's do that instead. I don't really need this. I'm going to group, right? All right, let's group. What can I take out of the first group?
X squared.
What's that leave me?
X plus 5.
Okay, what can I take out of the second group?
4. X plus
And I get x plus 5. So that's how I know grouping is going to work, is when those parentheses match up. Which means that x plus 5 now is a common factor that I can take out. And then what's left? Okay, So how do I get the actual zeros?
X plus 5 equals 0.
So x plus 5 has to equal 0. And x squared plus 4 would have to equal 0. Because we're really trying to find what are the values of x that would give us a 0 answer. Here, that's pretty easy. X is going to be -5. What's going to happen here, though?
X squared will have to equal -1.
So that means when I take the square root,
Plus or minus 2.
C.
so yesterday, when you were doing the review for the quiz, and you got to that point where you had the factor x squared plus 11, we said we didn't get any solutions from that factor because they would have been complex and the directions specifically asked for real numbers. But today, we're being asked for all answers, and so now the plus or minus 2i has to be included. We do work that out. We do get the complex answers, and that's part of our overall answer. So how far you go with getting your answers depends on what your directions are asking for. Okay? If they're just asking for reals, then we would not include this. We would just say -5 was our answer if all we were asked for were reals. But because we were asked for all, we need to include plus or minus 2i as well. And so now how many solutions do I actually have? 3. 1, the positive 2i is 2, the negative 2i is 3. And what was my degree? 3. So they match. Okay? Alright, let's take a look at another one. Am I going to be able to use a special method on that one? Yeah, no, I don't think so. I got 6 terms, I got x to the 5th power. I don't remember any special methods for that one. Alright, so now we got to go with our p over q. But the good news is,
Your Q is 1.
our q is 1, and there aren't that many factors of 14.
There's 4.
Right? So what are my p over q possible rational zeros going to be?
Plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 4.
Okay, so at least the list is a little shorter. All right, so at this point, we go back to our calculator. Maybe. Calculator. Okay, maybe not. Come on, give me something. Try this. Okay, well, let me try to reopen it. Go ahead and do it on yours, because mine's not coming up. Graph that. See what you get. Alright, give me a number I should start with.
Negative 1.
Negative 1. Okay, so negative 1 for k. Bring down the 1. Negative 1, negative 5, positive 5, 9, negative 9, 1, negative 1, negative 14, positive 14, 0. Ding, 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 we have a winner. And we also now have what degree of a polynomial? A fourth degree. Okay, so we're not really down to anything that I can do anything else with. So I'm going to need to use my synthetic division again with another k value using this reduced polynomial to keep going. Okay, so what's another number that seems like I should use? A 2. Now, when you chose number 1, what was going on your graph at negative 1? It was bouncing, right? It touched and came back down. What do we know about zeros when our graph bounces? It's happening twice, right? It has a multiplicity of 2, meaning that that 0 is happening twice. So when I see that on a graph, it also means that I can use negative 1 again. Okay? Now, you said 2, so we'll go ahead with 2, see what that gets us. Alright, so bring down 1, multiply by 2, add, multiply, add, multiply, add, multiply. There's our next 0. Ding, ding, ding. Now we're down to what degree? Cubic. And it's not really looking like a cubic that grouping is going to work on. So I need one more number to get me down to quadratic. So here's where negative 1 would come up again. Okay, I'm going to use negative 1 a second time so that I can get down to a second degree quadratic, which I can then finish out using quadratic methods. Okay, so bring down my 1, multiply, add, multiply, add, multiply, add. There's my next 0. Confirm that these really are zeros. And I now end up with a quadratic of 1x squared minus 4x plus 7. Now, is that a quadratic that I'm going to be able to factor? No, can't come up with any factors of 7 that are going to add to a negative 4. So if I can't factor, then my next option is quadratic formula. Okay, the good news is it's better than having to do completing the square every time. Right? Because the formula is already set up. It's just plug in the numbers and see what you get. Alright, so opposite of b, plus or minus square root b squared minus 4 times a times c all over 2a, which is just going to be 2 in this case. What am I going to end up with inside of the radical? Negative 12, because this ends up being 28, so 16 minus 28 is a negative 12. Now, Tuesday, we would have said, all right, we're done. Because on Tuesday, we were only looking for real solutions. Today, we're looking for all of them. So today, we got to keep going. So how do I simplify the square root of a negative 12?
You can take a
Negative 2i.
2i times square root of 3.
Times 5.
2i.
Okay,
Joke.
so 12 has a perfect square factor of 4 in it. So we can take the 2 out, and the negative means I'm gonna take that out as an I, and I'm left with just 3 inside the radical. Can I simplify that anymore?
Yeah. So it's plus or minus I, square root of 3 over nothing.
Okay, so ultimately then, what are my final answers?
Can you divide everything by
Negative 1,
Negative 1,
2, negative 1.
actually let me go back here a second. Negative 1, but how many times was negative 1 used? Twice. So sometimes you're gonna see that when they list negative 1, they'll just list it. Other times you'll see that they'll put a little note that it has a multiplicity of 2. Okay, just to emphasize the fact that we did use that twice.
Which one do you want us to do?
I think labeling the multiplicity would be good.
Can we use our negative 1 sign?
Sorry?
Can we just do like negative 1,
Yeah.
comma, negative 1?
Yeah, that's fine. That'll do
That's
too.
an easy way.
Yeah.
So negative 1 has a multiplicity of 2. What else do we use?
2,
A 2,
um,
and then a 2 plus or minus I squared of 3. And how many solutions did we end up with? 5. There's 2 there. Third one's there. And then I've got 2 here, the positive and the negative. So there's 5 total. And what was the degree? 5.
Yay. Gosh,
Okay? So that's kind of how you know when you're done. Is if you have the same number of zeros as what your degree was in the first place. Okay? So, is there a lot of work to this? Yes. Especially when it's a case like this where our quadratic doesn't factor for us and we've got to keep going from there with our quadratic formula. But again, think of how much worse this would be if I didn't have some of these tricks. Like if I didn't have the rational zero theorem to start out with. Like 7 is probably not a number we would normally think of as possibly being something to try. And we would tend to start thinking about a bunch of positive numbers and we wouldn't try negative numbers until. So the fact that this narrows it down helps us out. The fact that we can go to our calculator to look at where the x-intercepts are helps us out. The fact that we now know, based on behavior at the x-intercepts, whether we're really talking about something that just happens once, or if it happens twice, or if it happens 3 times. If you see that shelf, we might be talking about something happening 3 times. And the fact that we can divide out using synthetic division rather than long division every time to see what the next step would be. Okay, and if you get fairly comfortable with this, you can do it just like this, where you just keep building on the next reduced polynomial and just keep going with your synthetic division. You don't have to set up a new one for every time. Just keep going with it until you get down here to a quadratic. Once you get to quadratic, you use whatever quadratic method you need to get down to your final answer, and then list all of them. And don't forget that whatever you used up here is part of the answer. Question, please?
I was just gonna say, if you didn't, like, have your calculator and you didn't graph it, would you just go through all the terms and then redo all the terms?
Yeah, so
Oh.
there trying to decide whether to tell you this or not.
You should.
What was the question?
So she said if you didn't have your calculator, right, how would you know that -1 got used twice? Was basically the question. So she said, would you have to go through all your terms and when the other ones didn't work, like go through them again to see if something was a repeat?
I don't want to ever do that.
So there is something called upper and lower bounds. And there's a pattern you can look for to know that you can't get anything higher than what you just tried or anything lower than what you just tried. So with positive numbers, whoops, it's already small enough, come back here. With positive numbers, when I do the synthetic division, if I end up with the reduced polynomial coefficients there, that last line, if these are all, make sure I say it right, if these are all positive, then that means there's no way you can get anything bigger. Now, it didn't quite come out that way here, but if you had done 7, it would have. So if you had done, if you were doing it with no calculator, just trying numbers, when you did 7 here, this is going to come out all positive. That's going to tell you there's no reason to try 14. Okay? Because your number now tells you that there's an upper bound and there is nothing bigger than that that's going to work. Okay? So when it's a positive number out here, you're looking for all positive answers here that tell you nothing bigger works. Just stop. Okay? When it's a negative number, then what you're looking for is alternating signs. So if this had gone positive, negative, positive, negative, positive, if we'd gotten the alternating signs all the way through, then you would know there's nothing smaller, there's nothing more negative than what you just tried. So if you want to write that, it's not something you're going to be tested on or anything, but it is another little trick of if you have to do these by hand and you don't get a calculator to help you out, it's something you can look for to go, okay, there's no reason to go bigger than this number because this tells me nothing's going to work anyway. And there's no reason to go smaller, more negative than this number because this result tells me it's not going to work anyway. So that's something you can look for. It's called an upper and lower bound. The upper bound is for positive k's, and you're looking for all positive answers. The lower bound is for negative k's, and you're looking for alternating answers. Positive, negative, positive, negative. Okay? I would be willing to bet that in most cases, either your list is going to be fairly small, so having to try all of them isn't that bad, or it's going to be on the calculator part. One or the other is going to happen. Either you're going to have a short list, or it's going to be a calculator problem. Okay? So does this make sense? So really we're just building off what we've been doing the last couple days. We're just adding sort of the extra step of now we need to include any imaginaries as well. Up until now we've only been dealing with reals. Now we want to include any of the other complex numbers that might include imaginary numbers. Okay? But the process for doing it is still the same. Start with your rational zeros list. If you can't use one of the special methods, like our first one, if you can use grouping, use grouping. That's awesome. If none of the special methods work, start out with your list of possible rationals, start testing those, graph it if you can to get an idea of which ones to test, and just keep working it down until you get to a quadratic. Once you get to that quadratic, then you can shift into either factoring or quadratic formula, and if there's going to be some weird answers like imaginaries, that's probably where it's going to show up, is when you do the quadratic formula. Okay? All right, now, the other thing we need to be able to do real quick is go the other way. So if I give you a graph, or if I give you some sort of information that tells you here are zeros that we have, that we know are zeros of this polynomial, can you come up with the polynomial for it? Okay? And there's a couple of theorems that can help you out with that. And they're called conjugate theorems. The first one is the complex conjugates theorem. And what it says is that if f is a polynomial function with real coefficients, so nothing funky going on in our coefficients, we're just dealing with real numbers, and you find out that a plus bi is one of the zeros, then a minus bi has to also be one of the zeros. The conjugates, right? A plus bi, a minus bi, those are conjugates of each other. And so what this theorem says is if you know that one of them is of 0, the other one has to be also. There's never a time when you don't get the conjugate to also be a 0. Which, if we go back to this one, we saw that, right? We had positive 2i, we also had negative 2i. We go back to this one, we had the 2 plus an I square root of 3, but then we also had the 2 minus the I square root of 3. Okay, so that's what this first theorem is talking about. If you're given one, you know the other one has to also be a 0, whether they tell you or not. The other one is similar, but this is with irrationals. So this one sounds really weird, but this is what it basically comes down to. So this one says, suppose f is a polynomial with rational coefficients, and a and b are rational numbers such that, oh, that's supposed to be square root of b, such that the square root of b is irrational. In other words, b is not a perfect square, so when you take the square root of it, you get a nice answer. Okay? If that's the case, then same kind of thing. If I know that a plus square root of b is one of my zeros, then a minus square root of b has to be one of my zeros. Okay? Similar kind of situation with our complex theorem. If I know that a plus square root of b is a 0, then a minus square root of b has to be a 0 as well. Okay, I know not everyone's got this copied, but it's in your textbook if you want to copy the rest of it. But I want to get to just a quick example here before we run out of time. So what sometimes happens is they're going to tell you that you have certain zeros. Okay, so here they're saying we want to write a polynomial that has least degree. So in other words, assume none of them are multiples. None of them happen twice or 3 times or anything. It's the least degree, has rational coefficients, a leading coefficient of 1, so not multiplying everything by anything, and we know that the zeros are at 3 and at 2i. Even though they didn't tell us, we need to know that if I have 2i, that means I also have to have negative 2i. So this is a case where a would actually be 0. So this would represent a plus 2i. So a minus 2i also has to be a 0. But I have to know that. They didn't tell me. But if I don't know that, my answer is going to get really ugly really fast. So what that means then is that my factors are always x minus the 0. So if I have a 0 at 3, a factor is at x minus 3. Right? Same thing works even for the weird ones. If it's 2i, then x minus 2i is a factor. If it's negative 2i, then x minus the negative plus 2i is a factor. And then to get this polynomial, I just have to multiply this all out. Now, I strongly recommend to you that you start with the factors that have the weird stuff in them. Because with them being conjugates, we are basically going to be using the difference of signs pattern, right? So when I FOIL this out, my outsides and my insides are going to cancel, which is going to get rid of the weird stuff. And what's left then are just going to be nice little numbers that I can continue multiplying by with the rest of the factors that I get. So if I multiply this out, I'm going to get x squared plus, I'm going to write it out for this time just so you see it, plus 2i times x, but then minus 2i times x, and then a minus 4i squared. So my 2ix's cancel out. Beautiful. What's I squared give me? -1, so this really ends up being +4. So what I end up with here is just x squared plus 4. Then I can take that times the x minus 3, and that'll give me the polynomial I'm looking for. Okay? So always set up your factors with x minus whatever they gave you as a 0. And then if you have weird stuff like this, multiply those out first to get rid of the weird stuff, and then keep multiplying from there. Yes?
Why does the I cancel out the I squared?
Because remember, I squared is equal to a -1. Right? So this was a -4. I turned I squared into -1, so it ended up 1 or minus -4, which ends up being 1.
So much here.
It's a little bit heavy. Yeah, a little bit. Stuff with some. Do you not?
Homework's on Canvas. We'll see you on Monday. Yes.